Have fun.
Thank you. Good morning. So as a kid, I loved the science fiction books of Jules Verne and the movies of Jacques Cousteau. And some years later, after I learned how to code and how to make robots, I met a student who also loved Jules Verne and Jacques Cousteau. And we decided to make a robot together, our own version of the 20,000 Leagues Under the Sea Observatory. We called this robot Amour, which stood for Autonomous Modular Optical Underwater Robot. But building this robot was really about love. Amour was lovable, it moved nimbly, it could take awesome pictures in water, it could communicate them, all of this enabled by very advanced capabilities. Now, one very hot summer day off the coast of Singapore, we decided to see just how fast and far Amour could go. We were feeling very confident that day. And we decided to take down all the safety features of Amour to give it more juice. And then off the robot went. And we waited and waited and waited. But Amour never returned. We lost the robot and we were devastated. Now, the thing about science is that the first copy of an invention takes a long time to make, but subsequent copies are much faster. And it is also true that great failures teach us great lessons. So equipped with this wisdom, we went back to the lab, and within 90 days, we had 3 improved versions of this robot, of Amour. And we took it to water, and as we watched it do flips in the water, we started wanting more. And this is how we decided to create a different robot. You can think of it as the sibling of Amour, the soft robot fish, Sophie. This is a robot with a soft tail, and this robot is very agile. It can change the swimming direction in about 100 milliseconds, which is comparable to what real fish do. And it is called the escape maneuver because it allows little fish to escape the big fish who want to eat them. So we took the robot to the ocean, and there it is, the black spot on its face. It's a fisheye lens camera, and I'm right there next to it. We swam with it, and we watched it glide beautifully and elegantly by beautiful corals. And the robot saw many schools of fish with its camera, and it even found Nemo. So, it took us 3 years to make Amour, 2 months to make 3 copies of Amour, and today in the lab, we can make Sophie in a few hours. And this rapid change of pace may sound familiar to you, because just 2 decades ago, computing was a task reserved for the expert few. Computers were large and expensive and difficult to use. You really needed expertise. But today, the smartphone has democratized computation. In fact, computing is so normal, you don't even notice how you depend on it. And this raises an important question. In a world so changed by computers that help us with our computing work, what might it look with robots helping us with physical work? How much work would we be able to offload to machines to save lives and increase the quality of our lives? For example, I believe that autonomous driving will ensure that there are no road fatalities and will give all of us higher quality of life in our retirement, and will give us all the ability to go anywhere, anytime. It is not a matter of if, it is a matter of when. So imagine driving home from work in your autonomous car, knowing your vehicle has the smarts to keep you safe and the intelligence to make that ride fun. You pull over at the grocery store to pick up supplies for dinner, and a robot connects with your house, figures out what you need, and then later on passes a box with the items you need. And later on, when you get home, you pass that box to your kitchen robot, and you might even let the children help with the cooking, because even though they make a mess, the cleaning robots will clean it up. Now, this may sound to you like one of those cartoons about the future that never comes to pass. But that future is not that far off. Today, robots have become our partners in domestic and industrial settings. They mow our lawns, they clean our pools, they even milk our cows. And in the future, they will do so much more for us. And this is enabled by 3 interrelated technologies that are advancing. And these technologies are robotics, and you can think of robotics as the technology that puts computation in motion, gives machines the ability to move. And artificial intelligence gives machines the ability to have human-like characteristics, to hear like humans, to see like humans, to play games like humans, to communicate like humans. And machine learning cuts across robotics and artificial intelligence and aims to learn and make predictions from data. Now, all fields that have data can take advantage. And so, for instance, medicine is a great example. Machines today can look at more radiology scans in a day than a doctor will see in a lifetime. So in a recent study, machines and doctors were presented with scans of lymph node cells, and they had to label them, cancer or not cancer. The machine made 7.5% error as compared to the human's 3.5% error, but working together, the humans and the machines achieved 80% improvement at 0.5% error, which is really huge. Now, today, these systems are deployed in the most advanced cancer centers in the world, but imagine a day when these tools are available to everyone, to overworked doctors, to doctors in remote areas who do not have time to stay on top of the latest and greatest clinical trials. Everybody will be able to take advantage of the greatest work knowledge in order to offer us, all of us, the most personalized and effective treatment. Now, many of the things you hear in the media about machine learning and advances are due to techniques related to machine learning, and in particular to a technique called deep neural network. And in deep learning, we use data, a lot of data, usually millions of hand-labeled examples, to determine the weights in a very large graph structure, like the one sketched in this picture, so that when an unlabeled image like this one gets presented to the network, the system says it's a beach. So this process works by analyzing the data, and given today's technologies with images, the first step is to segment the image to figure out which pixels go with what object in the image. And this can be done by machine, so you can pass pictures into the network, and you get a lot of segmented data. And once you have this collection of segmented data, the objects in the picture have to be identified in order for the system to learn. And do you know how this is done? Well, this is how it's done. Lots and lots of people sitting in centers and manually labeling what those pictures represent. So I wanted to explain this to you because in addition to understanding how the technique works, it's also important to understand what it means for a machine to recognize an image. We say it's learning, but in fact learning means that the machine associates a set of pixels with a different set of pixels, some human labeled with a certain concept. But in the process of saying this is a beach, the machine has no idea what you do with a beach. What do you do with it? Do you eat it? Do you drink it? Do you play on it? How does it feel? None of that is associated with a beach at the level of machine learning. And so let me show you another example. Take a look at these two pictures, and let me ask you if they look the same to you. Well, they should, because they look the same to me. But in fact, they're slightly different. There is a little bit of imperceptible noise that is injected in these pictures. And this noise is enough to trick a network that correctly recognizes the first picture as a dog to recognize the same picture as an ostrich. So we are enabling a lot of new applications with these techniques. But these techniques are not perfect. And if you're going to use them or rely on them, you have to understand when they work, how they work, what kind of error they yield. So deep learning has enabled applications, but there are significant limitations. Take a look at this picture. So this is an 18-month-old that's watching the scene for the very first time ever. And look at what he's done. He's figured out what the adult wanted. He goes and executes an action to help the adult, and then he makes eye contact, as though saying, "Did I understand you?" So we have no machines that have the capability, this extraordinary capability of the human mind. We are working on some of these grand challenges, and we hope that in the future we will have some progress. But today's AI systems are not able to do what this 18-month-old is doing. So there are significant challenges with today's techniques, manual data labeling, obtaining massive sets, and bias in the algorithms. But there are also huge opportunities, like I have shown you in the medical case. And the opportunities are around personalization, customization, but with machines and people working together, because machines are better at some things than we are, and we are better at some things than machines are. Working together, we can do so much better. Now, working together, machines and people can also become better transportation systems. And in one of our recent research projects, we developed an algorithm that matches supply and demand. We applied it to taxis, and in particular to the traffic in New York City. And we have shown that we're able to remove about 11,000 cars from the roads of New York City and still provide a very comparable level of service of about a 3 minutes delay to when you get to the destination. So these techniques can really help us increase the quality of our lives. Now, if the vehicles become autonomous, we have the added benefit that we expect to remove road fatalities. And we are very much working on this problem. In fact, this is the MIT C-Sail autonomous car. Its body is a regular car, extended with sensors, LiDAR scanners, GPS, and cameras. And this car operates by driving in the world, by looking at what the sensors give to understand what's happening around it, by detecting where the obstacles are, localizing, and planning where to go next. So this autonomous driving pipeline is actually the pipeline that's adopted by most commercial companies. And in fact, there are some challenges, because every situation needs to be explicitly modeled for each type of situation, whether you're driving at night or you're driving on roads with or without lane markings, etc. So autonomous systems really need the ability to handle a wide range of scenarios. And in response to these scenarios, they just need to know what to do. Right now, we hand code everything. Now, in my research group at MIT, we are adopting another method, which is to learn from humans how to drive. So what we are doing is we're using a deep neural network engine, and we're looking at examples of how humans steer the car in certain road situations. And from that, we decide how to associate that particular image with a control system. And let's look at what we can do. This is my graduate student, Alexander. He's listening to country music, which I took out for this talk. But in this example, Alexander is telling the car, let's go. The car has a topological map of the world, so the map is very simple. It's literally what you see in the corner. And this is a first drive of the car on this road. The car was trained in a different environment. And just look at how easily and smoothly this car glides on the road and figures out what to do. Now, I tell you that I was involved in teaching my daughters how to drive, and their first drive was not as smooth as this car. So the car uses 3 cameras that uses left, center, and right cameras, and the images from these cameras are fused. And when it comes upon an intersection, it's able to look at special cues that it finds, special features that it finds in the images to figure out what to do. So it's very exciting. I think that although we don't have level 5 autonomy, we do have robust autonomous driving that could be deployed immediately in places like villages, in places where we have a low complexity in the environment, fairly low driving speed. Now, here's another awesome thing we can do. The same technology for autonomous driving can be mapped onto wearables, where the laser scanners become belts and the cameras become necklaces. And with this, we can provide blind and visually impaired users to safely navigate the world. So with this system, a blind user can walk down the street and get a fabulous description of a fabulous window display, or a warning of a presence of an obstacle, or that a friend is going by. So we can use this technology to replace the walking stick and provide blind people and visually impaired people with the kind of flexibility and ease of movement in the world that is simply not possible today. So here's our blind user who's used the system and has found a way to get to a bench, sit on it, and feed the duck. The system will tell the user when the ducks are going by. So we're making great technological advances, but in order for these advances to be broadly used, people and machines have to be able to work together without knowing precisely what happens under the hood. You can drive your cars without understanding every component of the engine. So how can we get there? One interesting question we're posing in my research group is, can we get to a point where machines adapt to us rather than the other way around? Because today we are adapting to machines in that we have to learn how to program them. So the question is, can we connect our ideas and our desires directly to the machine? And the answer is that in general, no. In general, the kind of sensors we have to listen for brain activity are too impoverished to make sense of our brain waves. But there is one type of thought, of brainwave pattern, that we can detect reliably. And this is what our brain does when we see something that is wrong. It is the "you are wrong" signal. It's not trained, it's the same no matter what language you speak in. So by detecting the "you are wrong" signal, we are able to connect people with machines directly in a very simple scenario, but this is the beginning of what might come. So here's our user wearing an EEG cap, and through this EEG cap, we have 48 electrodes that measure brain activity. And we have a robot that's tasked to sort paint can and wire spool. Paint goes in one box, wire goes in the other. And when the robot makes the wrong move, the user thinks, oh, that's wrong. That triggers the special error-related potential, and that allows the robot to move over to the other box. So here, the robot made a mistake. The user detected it, and look at how the robot changed without any kind of actual programming intervention. So there are some very exciting opportunities for AI, machine learning, and robotics for the future. And I really believe that with these technologies, we will reduce and eliminate car accidents. We will better diagnose, monitor, and treat disease. We will keep your information private and safe. We will transport people and goods faster and more efficiently and safer. We will deliver education to everyone. We'll ensure that people can connect to one another instantly, globally, no matter what language they speak. In general, we will allow humans and machines to work together, with machines doing routine tasks and humans focusing on the high-level, critical thinking, strategic tasks. The future is great. Thank you very much.